This is the beginning of my series on electrical power transformers. You can find this topic in my course entitled Electrical Three-Phase Power Transformer Fundamentals. You can access this and my other courses in my Stan Store at this web address. Before proceeding though, I want to remind you of 𝐃𝐈𝐒𝐂𝐋𝐀 sale that is only running from July 16th to July 17th, which they call their Prime Day Big Deals. More immediately though, you'll find up to 9% extra discounts, a 30-day price match guarantee, interest-free installments, and some benefits for members only. You can check out these sale items immediately at this web address. Keeping this concept in mind, I would like to explore and compare the speed of electricity and the speed of electron flow. Looking at this example of an electric circuit made up of a battery and a resistor and a switch. If we close the switch, there seems to be an instantaneous movement of electrons at every point in the circuit. However, this is not quite instantaneous, but it is very close. It depends on a lot of parameters such as the wire size and the length of the wire and the battery voltage and the temperature, and a lot of things depend on exactly how fast the speed of electricity is. However, it is always very close to the speed of light, which is 186,000 miles per second. Now, if we open the switch, the reaction speed is the same. The electricity will stop flowing almost instantaneously, or close to the speed of light. However, this is not the speed of electron flow, which is often referred to as drift velocity. And as I said, this is not the speed of an electron flow. An electron is not flowing at the speed of light. In fact, if we were to compare the speed of an electron flowing in a wire to that of a common garden snail, the garden snail would hands down beat the electron in a race, because the garden snail moves at about half an inch per second, whereas an electron moves in the wire at about 0.0028 inches per second. So, what's going on here? How can electricity seem to move at the speed of light, yet an electron flow is slower than a garden snail? In order to answer that question, I'm going to again zoom in to the subatomic level and consider what's going on in a wire, in this case in a two-dimensional fashion, 3 atoms by 10 atoms, as you can see. There's a positive charge on the left-hand side and a negative charge on the right-hand side, which would be indicative of connecting a battery with a positive end on the left and a negative end on the right. As you can see, electrons seem to be moving freely about, but if you watch for a while, there seems to be a flow or a drift from right to left. Some electrons, however, seem to be moving left to right, but that is because they are bumping into each other. And actually, they're not actually bumping into each other. They're coming close and being repelled into the opposite direction, which looks like they might be bumping into each other. But there is a general net flow from right to left. Now, if we multiply that net effect by 6.25 million, you would see that there is definitely 1 amp flowing in the circuit. But that still doesn't necessarily explain the instantaneous reaction. For that, let's move on. Consider what is often referred to as Newton's cradle. And I'm sure you've all seen this at one time or another. A lot of people have them decorating their desk. You can see that you have a metal ball at one side, and as that ball swings in, it connects to the next one, which connects to the next one, which connects to the next one, and pushes off the one on the end. And that reaction, or that flow of action, if you would, seems to be taking place very quickly, in fact almost instantaneously. However, the ball is not quite moving from left all the way to right, but the action itself is moving from right to left. Now, let's take a look at, and this again, I apologize for the crude animation, but let's assume we're looking at a bunch of electrons in that wire. What is happening when you close the switch? You're actually pushing one electron into the bunch, and almost instantaneously, at the speed of light, an electron at the other end flows out. And what's happening is they aren't colliding, as I said, but they are electrically charged. So you're actually getting a electrostatic wave going from right to left. And that is happening at the speed of light. The electron itself is not flowing down the line. It is moving, but it's the actual action or the wave of electrostatics that's moving down the wire, and that is what electricity is. So I hope this crude analysis helps you visualize what is actually going on in an electric circuit. This video is part of my electrical technical information series. Be sure and stay tuned, as I will also from time to time be reviewing electrical products that in my opinion are worthy of paying attention to. This address will give you access to the supplier of aforementioned products, and it is also the connection to obtain a free copy of my 50-page electrical power crib sheets.